today what we're going to do is we're going to dive into the integrated rate law, the Arrhenius equation, and reaction mechanisms, and what those tell us. So, the integrated rate law, essentially what we do is we use calculus. So for integrated rate laws, we use calculus to derive a relationship that allows us to determine the specific concentration of a particular reactant at a given time. So if we talked about, say, like for example, a first order integrated rate law. So the first order rate law would be just like rate equals K times the concentration of A to the first power, right? That's what a first order rate law is. Okay. You could also see rate sometimes written like this. Rate is equal to delta concentration of A. And actually usually because rate laws given in terms of reactants, this would be negative delta A over delta T. And specifically because this is a first order integrated rate law, that means that the equation that you're dealing with would probably only have one of these, so it would be 1 over 1 as the fraction. So delta A over delta T. So what can basically happen here is you can set these two rates equal to each other, and you get delta A, or rather delta A, KA is equal to negative delta A over delta T. Okay. In calculus, though, we represent deltas or changes as infinitesimally small, and so it would just be like it would be dA over dt, and that's equal to K concentration of A. So what you end up having happen here is essentially I multiply both sides by delta T. And that gives me delta A is equal to, or negative delta A I should say, is equal to Ka dt. I can then divide both sides by the concentration of A, and if I do that, I get K dt is equal to 1 over concentration of A, or negative 1 over concentration of A, times dA. And then at this point, I integrate both sides. This is calculus. I integrate both sides across T final minus T initial, which is, just put 0, and integrate this across A final A at time T divided by A initial. Okay. Well, one of the things you'll notice here, I can pull the negative sign out in front when I integrate like that, and this is going to give me 1 over. Actually, not. When I integrate 1 over A, it actually gives me the natural log, right? Because the derivative of natural log of concentration of A is 1 over A. So inverse, if I integrate 1 over A, it gives me the natural log of A. So this essentially is going to be, this integrated is going to be natural log of A at time T minus the natural log of A initial. However, there's that negative sign in front, which I pulled out before, and all that is equal to KT times KT minus K0, because in this case, dt, that's just going to be dt, that's going to, when you integrate with respect to t, because K is a constant, I can pull constant out, that's just going to integrate to t, and you're going to end up with KT minus K times 0, which is just basically KT. Rearranging this a little bit, you get your first order integrated rate law, which is essentially the ln of A at time t is equal to negative KT plus the ln of A initial. Now, do you have to know that calculus? Not really. It's not essential that you know the calculus, but I wanted you to understand where this integrated rate law comes from. What this allows you to do now is calculate the precise concentration at any given time, which is not something that you could do easily before. It's not something you could do easily with this, because this is more kind of like average rate, average concentration change, etc. And it's not something you could really do with this either. So if you know, this allows you to compare the concentration you start with to a concentration later on at a given time. Alright, so there are 3 integrated rate laws, and you'll see them on the back of the page that I gave you. And the 3 integrated rate laws are as follows. Just for the sake of tranquility, Alright, so the 3 integrated rate laws are as follows. You have the 0 order integrated rate law, which is basically just the concentration of A at time t is equal to negative KT plus the concentration of A initial. There is the first order integrated rate law, and that is the ln of A at time t is equal to negative K times T plus the ln of A initial. Okay. And then you have the second order integrated rate law, which is 1 over A at time t is equal to positive KT plus 1 over A initial. Okay, so these are the 3 common integrated rate laws that you deal with in lab or on test. You're not going to have to worry about a third order integrated rate law, although we could use calculus to solve for it if we really wanted to, but I don't think you want to, and I don't either, so let's not. Essentially, the usefulness of these is that you might notice that each one of these is written in y equals mx plus b format. Y equals mx plus b. Now, the usefulness of these is that when you are in lab, or if you're a scientist and you're actually trying to devise what the rate law is for a particular reaction, you can actually graph A versus time, ln of A versus time, and 1 over A versus time. And depending upon which of those graphs gives you a straight line, you will be able to tell which one, or what the order of reaction is. So for example, let's say I have 3 graphs. I did an experiment and I'm graphing A versus time, ln of A versus time, ln of the concentration of A versus time, and I'm graphing 1 over the concentration of A versus time. And this is what I get. What is the order of reaction with respect to A? Second order. The only one that actually gives me a linear relationship is the second order graph, which means this reaction must be second order. if it was zero order with respect to the substance, this should have been a straight line. It's not. If it was first order with respect to the substance A, this should have been a straight line angled downwards. It's not. Actually, sorry, this would have looked like this, actually. But since it ended up happening to be the 1/A graph that was a straight line, that means that was the order of reaction with respect to that substance. Now you're going to be doing a lab very soon in which you're going to actually make use of this. I don't know if you've done it yet. Have you done the crystal violet lab? Okay. So in that lab, you graph 3 of these, and whichever one gives you the best straight line, that tells you what the order of reaction is with respect to it. Now, the tricky thing about this is that you have to make sure that the reactant you're looking at is isolated. In other words, you have to make sure that everything else is such a large concentration by comparison that it's not really going to change. Because if it's not, then you're going to have interference from those other things that may also make this look like it's a different order of reaction. Okay, so let's take a look at some of the problems that we've come across with this. And these would be more like lecture-based problems or homework-based problems. But it says the first order, so problem number 4, P4, it says the first order rate constant for the decomposition of dinitrogen pentoxide is given as follows at 70 degrees Celsius. And that first order rate constant is 6.82 times 10 to the negative third. Suppose we start with 0.0250 moles of N2O5 in a volume of 2 liters. How many moles of N2O5 will remain after 2.5 minutes? Okay. So the first thing we ought to notice here is that it actually tells me that I have a first order reaction, right? I have a first order reaction. Because I have a first order reaction, that means I'm going to use the first order integrated rate law. The other thing that tells me that I want to use this instead of like one of the other rate laws, like, because theoretically, I mean, I really could just use this, couldn't I? I could use rate equals K times concentration of A. Because that is first order, isn't it? Why would, what clues me out, that clues me to the fact that I'm not going to want to use this? Any idea? That's okay. It's a little bit tricky if you're not looking for it. Essentially, it gives you the initial concentration, but it's not asking for the rate. It's asking for the concentration later on. Now in this case, if it gave us the initial concentration and it wanted to know the rate, then we'd use this. Because if we had the initial concentration, we could calculate the rate by plugging in the rate constant. Right? But in this case, it's asking us for the concentration at a later point in time, after 2.5 minutes. So this is not going to help us find a concentration later on. For that, we need to go to the integrated rate law. Does that make sense? So, if we have 2 times, and especially because time is not part of that other rate law, right? Time is only part of the integrated rate law. So, I'm going to go ahead and list out my variables here. I have my concentration at time t, which is actually kind of what I'm looking for. And then I have my concentration initial. And then I have my rate constant k. And I have my time. And that's about it, right? So what time am I looking at? What time am I going to use here for part A?
Minutes?
Yeah, the 2.5 minutes, right? 2.5 min. What's the value of K here?
$6.82.
6.82 times 10 to the negative third. And also make sure you write the unit, seconds to the negative 1. Now what's my initial concentration? Does it give me that?
0.025 mole.
Close. It's 0.0250 moles per 2 liters. So that's actually going to be 0.0125 molarity. Alright, and it looks like what I need is this. So I'm solving for that. I'll probably want to use this because that'll make it easier to solve for a at time t. So I plug it in, so I'll be like ln of a at time t is equal to, oh, but you know what, I just noticed something. Always compare your k and your time. What's the problem here?
Seconds.
Yeah, so I'm going to go ahead and convert this to seconds real quick. 1 min is equal to 60 seconds. And that's going to give me, let's see, 150 seconds. So, 2.5 times 60, that'll be 150. So now I can go ahead and use this equation. Negative k is 6.82 times 10 to the negative third, seconds to the negative 1, times 150 seconds plus the natural log of 0.0125 molarity. Now what does that give me if I multiply it up?
Negative 5.4.
So negative 5.4, anything else? Got
0.35.
Yeah, 5.40. 4. We'll leave it at that for now. Technically speaking, it would only be. Actually, no, I think that would be about right. That would be about right. Alright, maybe a little bit less. Okay. Alright, so now here's the thing. This is ln of a at time t. If I want to solve for a at time t, what do I have to do? What's the inverse of natural log? E. So I have to do e to the power of both sides. E to the negative 5.404, and the e to the ln will cancel that out, and I'll get a at time t is equal to what? What'd you get?
0.004.
0.004?
Yeah.
I got that too.
I need a couple more sick things.
4, 9.
Or
After this 4 and 9.
9. That would have been 0.005 then if you had rounded to that. What's after the 9?
It will be 0.0045.
It's
It's 449.
449, okay. And so that would be the molarity. Now here's the thing. This would in fact only be two significant figures, because technically speaking, this should only be about two significant figures. Well, it looks like it should be 3. But the thing is, when you take e to a power, that number before the decimal is actually not significant. Only places past the decimal are significant when you do logarithmic values. So e to that power, since this is a power, the numbers after the decimal are the ones that are significant, so you have two sig figs, it'd be 0.0045. It's one of those weird rules with significant figures when using logarithmic values. Honestly though, probably your professor's not going to care one way or the other, so shouldn't have said that out loud. But anyway, so now you have 0.0045 molar, but it's actually asking for how many moles of N2O5 will remain. So to get the moles, you would just multiply by the volume, which is 2 liters, and that would give you your moles of 0.0090 moles.
multiply that by 2 liters.
Yeah, because effectively it's 2 liters, and then since this is the molarity, it would be 0.0045. Molarity means moles per liter, moles per 1 liter. And liters cancels out. You get 0.0090 moles. Now, for part B, it then asks us how many minutes will it take for the quantity of N2O5 to drop to 0.010 moles. Quantity of N2O5 to drop to 0.010 moles. Now, in this case, we could consider using a different version of the integrated rate law. Is it okay if I erase this?
Yeah.
Okay. So, one thing you may or may not remember, because let's face it, we don't use logarithms a tremendously large amount in a lot of our math classes. One thing you may or may not remember is that if I subtract ln of a naught from both sides, if you have one logarithm minus another logarithm of the same base,
Divide.
yes, I can actually rewrite this as ln of a at time t divided by a naught. And that would be equal to negative kt. Make sense? Cool. So, in this case, this form of the integrated rate law is actually going to be more useful for us since we're actually solving for time now. But you could still use this version if you had wanted to, it just would take a few more steps. Also, there's another advantage here. Since the volume is the same, the concentration ratio is the same as the mole ratio. So let me explain it like this. So if you have molarity over molarity, right? Even if the molarities are different, let's say this is molarity at time t and this is molarity initial. Well, this would be the moles at time t divided by the volume, which is 2.0 liters, right? But the volume hasn't changed, so at this point in the reaction, it's the moles initial divided by, we'll say moles initial, divided by the 2.0 liters, because the volume hasn't changed, right? So in both of these cases, since the volume is 2 liters, that part really cancels out. And you see that the mole ratio is really the same thing as the molarity ratio. Does that make sense? So when you're using this like this, you can actually, if you want to, you can actually use moles or molarity. You can even do that for this up here. As long, but the only reason that it works here is because this equation can be manipulated into this form so that you get the molarity ratio. Well, that's the thing you got to be careful of. Unless you could convert this equation into this form, you would not be able to use this. But, alright, so now let's go ahead and solve for this. It wants to know how long will it take N2O5 to drop to 0.010 moles. So I'm going to actually use the mole ratio instead of the molarity ratio. And so this will be ln of A at time t, which is the amount 0.010 moles. That's the final amount. And divided by the initial amount, which was 0.0250 moles. And that's equal to negative k, which I know is 6.82 times 10 to the negative third, seconds to the negative 1, times t. So all I have to do here is solve for t. So I just divide both sides by negative 6.82 times 10 to the negative third, seconds to the negative 1. And that's going to clear this out. This. I'll divide that on this side as well, negative 6.82 times 10 to the negative third, seconds to the negative 1. And of course, this top part is going to be unitless, but if I divide by seconds to the negative 1, it's going to flip to seconds. Which is good, because I'm solving for time, so I should get a unit of time, like seconds or minutes. Well, what does that give me if I calculate that?
I got 134.35.
134.35 seconds. Now, is that reasonable, given the answer from the previous problem? Is that reasonable?
No.
Why not?
Because we need to change it to minutes, because it's asking how many minutes will it take.
Oh, well, that's a good point. But, so if we converted this to minutes, so divide that by 60 seconds, what do we get?
2 minutes and 14 seconds.
Or you could just say, is it 2.14?
2.2.
Yeah.
2.1?
2.2. Yeah, 2.24.
2.24? Yeah, and that would be about 2 minutes and 14 seconds, so 2.24 minutes is fine though. Now here's the thing though. In the previous problem, part A, it took 2.5 minutes, right? It took 2.5 minutes, and what was that amount, the most that was remaining after 2.5 minutes?
0.009.
0.009. Here, it took 2.24 minutes less time to get to 0.01, which is just a little bit above 0.009. So is that reasonable? It actually is. Because if I let it go just a little bit further to 2.5 minutes, it'll drop it a little bit further to 0.009. So this one way you can check your answers for reasonableness. Now if I had gotten something like this, if I had gotten something that was like 3.5 minutes, I should be very suspicious. Because if
How's it gonna?
yeah, because if it was 2.5 minutes at 0.009, how is it going to take 3 minutes to get to a higher one, right? So you can check yourself, and a lot of times if you think about these things, you can actually recognize mistakes before early on. All right. So I want to get to. We may come back to more of this. Oh, let's do C first. It says, what is the half-life of N2O5 at 70 degrees Celsius? What is the half-life of N2O5 at 70 degrees Celsius? Is it okay if I erase this? Yeah. So, you'll notice on the page that there is actually an equation for half-life for each one of these integrated rate laws. Now, I'm not sure if in fact he's going to give you those or not, or your professor's going to give you those or not, but honestly, if you did need to solve for the equation for half-life, it would actually be very simple. You could simply plug in x for the initial concentration and half x for the final concentration, and then solve the equation for that. Because the x's would in fact cancel out, and you'd be able to solve for it for the half-life equation. But the half-life equation is given on that sheet there, and you can take a look at it. In this case, for a first-order reaction, the half-life is equal to the ln of 2 over k. Okay? The ln of 2 over k. You'll notice that this is the only half-life that is not concentration dependent. The half-life of a zero-order reaction is, I believe,
Concentration of is A initial over 2K.
over 2k. Yeah. And the concentration for a second-order reaction,
It's 1 over K concentration of A initial.
would you say it was?
1 over K times concentration over of A initial.
And there's not a 2 there?
No.
Yeah. So, the half-life for a zero-order reaction gets bigger with the bigger initial concentration. The half-life for a second-order reaction gets smaller with a larger initial concentration. A first-order reaction is the only one where it doesn't matter how much you start with, it's still going to take the same amount of time to cut to half. Very interesting. So, with this, now I can go ahead and solve for the half-life of N2O5. It's actually very simple, because all I really have to do is plug in the K value here. So T1 half is equal to the ln of 2 divided by 6.82 times 10 to the negative third seconds to the negative 1. And if I do that, I'll get my half-life, the time it takes to go down to half. Should be somewhere in the neighborhood of about 2 minutes.
Got 101.634.
Yeah, about 101 seconds. 101 seconds. 101.6, so that'll be 102 seconds. That is the half-life. That's the half-life of that reaction. Now, problem number 5 is similar to this one. It deals with absorptivity, absorbance. And while that is important, it's not as important that I want to focus more time on it because I'm not sure if I'm going to get through everything else. So I want to go skip ahead to problem 6. It gives data for different reactions. So in reaction kinetics, we have what are called, I guess you could say, energy diagrams, or potential energy diagrams that kind of indicate what's happening at each point in a reaction. And so these will be very important once you get to organic chemistry. So I do want to take some time to look at those. So, for example, in this reaction, your typical energy diagram, if it's a one-step reaction, what you'll notice is that if the reaction is exothermic, typically you'll have this activation energy and you'll have a different change in energy here. So on the bottom, or this is usually the potential energy. The potential energy, the chemical energy of the particles are involved in the reaction. And this is either time, or sometimes referred to as reaction coordinate, or progress of reaction. Some will call it time or progress of reaction, as the reaction goes to completion. Okay. So there's several key features of your standard graph that I want to draw your attention to. There's this one spot at the very top, the highest part of the hill. This is referred to as the activated complex. It's the highest energy state of the entire reaction. This is the energy that it needs to reach if it is going to react. If it can't reach this level of energy, it will not react. It'll start, but it might just fall back down. It's not going to be able to reach that point. It's kind of like what we were talking about before with the collision theory of reaction. If I have, two atom molecule A, B, and C wants to come in, and it comes in at the right angle to collide with this and knock B out. But if it doesn't have enough energy, to create the activated complex, it's just going to bounce off. It's not going to form. The reaction does not happen. All right. But once it gets up to this energy, then the reaction happens quickly, rapidly, and releases a lot of energy, as you can see. That downwards part of the energy graph means all that energy is released. So the net change in energy for the reaction is, and actually I should just not draw a double arrow in this case, it's going to go down. This is the change in energy of the reaction. All that energy that's lost, because this is the energy of the products, this is the energy of the reactants. That energy that was lost is typically given off as heat, or given off as work. It can be either heat or work. If you remember from, which you're going to actually have to brush up on pretty soon because it's in an upcoming chapter, but remember that delta E is equal to Q plus W? The change in energy of a process is equal to the heat plus the work? That's what happens there. So the reactants have a higher energy, then this is what's called exergonic. It releases energy, and you have lower energy products. And most reactions are like this because reactants, chemicals, substances are always trying to get to the lowest energy state possible because they want to be stable. Alright, now, this amount of energy here, though, this amount of energy here from the starting point to the top here, this is what's referred to as the activation energy. Activation energy. As the amount of energy that you need to add to the reactants to get it up to the activated complex and make the reaction happen. So now that we have a basic idea for what these reaction diagrams look like, let's actually draw 3 reaction diagrams for the 3 reactions described in problem 6. So first, it says reaction 1 has an energy of activation of 45 kilojoules per mole. I'll set my energy and my time. So here's my reactants. And I have 45 kilojoules per mole as my activation energy. So I'm going to have to drive this up a bit, right? So the distance I know between my initial starting point and my highest, this is going to be about 45 kilojoules per mole. Right? Now it says the delta E is negative 25. So when all is said and done, the product is actually going to be lower than my initial reactants by about 25. So, that means my delta E here my line should be lower. Be lower than this. Lower than the starting point. Okay. Well, so now let's draw another one for reaction 2. So this is that was reaction 1.
So we go to the top, right? No, not reaction 1, reaction 2.
What'd you say?
Oh, never mind, I got confused with the third.
Okay. So here's another energy, here's another time. And the activation energy in this case is 35 kilojoules per mole, so it's not going to go quite as high. Say, assume it starts from about the same position. Not quite as high. But now the delta E, it says, is negative 10. When it drops back down, it's not going to drop as low. It's not going to drop as low. And then I'll draw my.
So it would be 10 lower than the initial, or is it 10 lower from the?
Yeah, so it's 10 lower than this one. Oh yeah, this here is 10 lower than the initial.
Okay.
So the delta E here is equal to negative 10 kilojoules per mole. The activation energy is positive 35 kilojoules per mole. Alright. And then last but not least, we have reaction 3. And this is now where I'm wishing I had made my graph smaller. Okay. Alright, I'm just going to do this. And be slightly ridiculous, but I'll just pop it up here in the corner. Alright, so here is E and time for reaction 3. So let's say it starts at the same level, goes up to 55 kilojoules per mole. So EA goes up, whoa! But then it's positive 10
Right.
delta E. So, the interesting thing here is that activation energy for this is a staggering 55 kilojoules per mole. And this appears to be an endergonic reaction, possibly endothermic, because the energy actually increases. Delta E is positive 10 kilojoules per mole. Now, the question then says which of the reactions below will be the fastest in the reverse direction? The fastest in the reverse direction.
Wait, E? I mean the third one?
So if it's in the reverse direction, that means that your activation energy is from your product energy to the top of the activate complex. So what is the activation energy for the reverse reaction of reaction 2?
25.
45.
Oh, so it's 45.
Yeah, because it'd be like, you have to go up 10 and then you have to go up another 35.
Oh, okay.
So that'd be 45 kilojoules per mole for the reverse reaction here. What's the activation energy for the reverse reaction for reaction 1?
Uh, 70?
70, yeah, 70 kilojoules per mole. Then you have to go up 25 and then another 45, so 70 kilojoules per mole. What's the activation energy for the reverse reaction of reaction 3 here?
Action 3.
Reaction 3.
Oh,
65.
no, 45.
Oh, 45. 45, yeah, because it's
it's
already up
positive
10.
Oh, okay.
So I don't have to go up the whole 55, I actually only have to go 45 in the reverse direction.
And you said it's called activation energy?
Yep.
Okay.
Now, which one would be the fastest in the reverse direction?
Option 2.
Well, both reaction 2 and reaction 3
45.
have 45.
So it's both of them.
They're both about the same, except this one might have a little bit of an advantage because in the reverse direction, this is what?
Closer to the...
Exothermic, or exodromic at least. And in the reverse reaction, this would be endo. So, but the speed of the reaction is really more determined by the activation energy than anything else. And so, because of that, you could assume that both reverse reaction of reaction 2 and the reverse reaction of reaction 3 would be about the same speed. That's good. And then of course, you know which one would be the slowest. That would be reaction 1, would be the slowest in the reverse direction.
70 kilojoules per mole.
Which would be the quickest in the forward direction?
So the forward direction
Reaction 2?
is going where?
Well, the forward direction of the reaction is the way the reaction is shown. Like this is time as the reaction proceeds. In the reverse direction, you kind of treat it as going backwards, but in the forward direction, just be as shown.
Okay.
So which one would be the fastest going forward? See, reaction 2, that's right. Because this only has a 35 kilojoules per mole activation energy, whereas this one has 45 and this one has 55. Now this one might be more favored overall, but this one is probably going to be a bit faster.
In the forward direction.
And then which reaction would be slowest in the forward direction? Yeah, reaction 3. Does that make sense?
Yeah.
So that's reaction kinetics in a nutshell. Alright. Now, the Arrhenius equation is based on this, because this activation energy, EA, this is actually part of what we're talking about when we're talking about the Arrhenius equation. let me write down what the Arrhenius equation is. Is it okay if I erase this? The Arrhenius equation is basically this. The ln of the rate constant at time 1 over the rate constant at time 2 is equal to the negative EA over R as 1 over T1 minus 1 over T2. Although actually, if you take out the negative, because you don't want to use negatives, I understand, you can actually switch these and that'll take out the negative. It'll be T2 to minus T1. Okay. Now you can of course switch these numbers too. You could say K2 over K1 and then this would be T1 over T2 and T2. But effectively, the one on top, if there's no negative sign here, the one on top should match the one that you're subtracting. And the one at the bottom should match the one that you started with. Does that make sense? Okay, so now this is actually the 2-point form of the Arrhenius equation. The original form of the Arrhenius equation is just simply the natural log of the K value is equal to the negative E energy of activation divided by RT plus C, some constant. Okay? And what this means is that the rate constant actually goes up considerably when, well actually the rate constant goes down considerably with the larger energy of activation, because since this is negative, that's actually going to make this a smaller fraction. The rate constant is going to be a smaller fraction. However, if you increase the temperature, you minimize this energy of activation factor. So the higher the temperature is, the larger K is going to be. Does that make sense?
Yeah.
And this is the reason for that. At any given time, you might think, well, temperature, you know, is a measure of the average kinetic energy of particles, right? Or if you didn't know, now you do. Temperature is a measure of the average kinetic energy of particles, but that's just an average. Let's say, for example, if I'm looking at the energy of all the different particles, this is a particle distribution, okay? Okay, so let's see. Energy distribution. So this would be the different amounts of energies. So this would be relatively high energy, and very high energy, and on this side would be low energy, okay? And this would be the number of particles having, number of atoms or molecules having that energy. So if we have a low temperature, like say 20 degrees Celsius or 0 degrees Celsius, the energy distribution curve looks something like this. So I have like that. So that would be like, say, that could be an energy distribution curve at say 20 degrees Celsius, okay? Most of the particles have this lower amount of energy, and only a few have this higher amount of energy, okay? However, let's say you had something at like 140 degrees Celsius, okay? You're actually still going to have a fair amount of particles at lower energy. But you're going to have a much broader spread. There's going to be a lot of particles that are at the higher energy. So this would be like, say, at 140 degrees Celsius, okay? Does that make sense? Now here's the thing. The energy of activation is a specific energy, a specific amount of energy that you need to have to react. So let's say if the energy of activation is like right here. Let's say the energy of activation is this point. That means only molecules with at least this much energy or more will be able to react. So if you look at this, at 20 degrees, only a tiny fraction Only that little area shaded in green will be able to react. However, at 140 degrees, all of this will be able to react. All of it. And you can see that this area here is well over 10 times what this tiny area is. So that's going to increase the rate of reaction by a factor of 10. Okay? So what this equation does is it relates the effect of temperature on rate of reaction. Because if you increase the temperature, there's more atoms that have the energy to react, and then the reaction will happen faster. If it's colder temperature, there's fewer atoms that have the energy to react, and therefore the reaction will be much slower. And so a rate constant is effectively directly proportional to how fast the reaction goes. Okay, so let's take a look at question 7. It says, understanding high temperature behavior of nitrogen oxides is essential for controlling pollution generated in automobile engines. Decomposition of nitric oxide, NO, to form N2 and O2 is second order with a rate constant of 0.0796 molarity per second at 737 degrees Celsius and 0.0815 molarity per second at 947 degrees Celsius. Calculate the activation energy for this reaction. Calculate the activation energy for this reaction. So in this case, I'm given 2 points, 2 rate constants, and 2 temperatures, and I need to calculate EA. Now here's the deal. When doing this, I have to make sure that I recognize that I will always, anytime I'm using temperature in chemistry, always the temperature must be in what form?
Kelvin.
Kelvin, exactly. The only time you can get away with Celsius is if it's a delta T, a change in
temperature.
Yeah, because the change in temperature in Kelvin is the same as the change in Celsius. Okay, I'm going to erase this now, right? Okay, cool. So this equation is a little bit of a beast to work with. It's not that it's necessarily very hard, it's more that you have to be very careful with your algebra or you'll make a mistake and it'll get thrown off. Alright, so here's what you can do though. I like to solve it piece by piece. This is one of those few that I don't believe in going ahead and solving it for EA first, because you could. But that would be a lot to put in. Okay. Oh, okay, well, let's do it anyway. Alright, so if I divide both sides by 1 over T2 minus 1 over T1 quantities, 1 over T2 minus 1 over T1. That cancels out this, and then I get EA over R. Okay? So EA over R is equal to this monstrosity, ln of K1 over K2, divided by 1 over T2 minus 1 over T1. Now all I have to do to solve for EA is multiply both sides by R. And bam, I have EA is equal to R times the ln of K1 over K2 all over 1 over T1 or T2 minus 1 over T1. The danger that sometimes people run into here is trying to put this all into the calculator at once. Because unless you have a really, really good handle on calculator notation and when not to use parentheses, you're probably going to make a mistake. Does anybody here feel so very confident with their calculator notation that they would want to throw this in
No.
all in one? Yeah, me neither. So what I would recommend doing in this case is solve for what's inside the parentheses first, and then put those numbers in, and then do the calculation from there. So in this case, the R value that you're going to be using is essentially the ideal gas law constant, which is 8.314 joules per mole Kelvin. That's your R value, 8.314 joules per mole Kelvin. And then I have the ln, the natural log, that times the natural log of K1, which is 0.0796. Now the truth is, you could use either one as K1, but you have to be consistent that the K1 and the T1 go together. So if I choose the 0.0796, if I choose the 0.0796 as my K1, that means my T1 is what?
137 plus 273.
There you go, exactly. This is 0.0815 molarity per second, and then I divide that by 1 over T2, which is going to be 947 plus 273. That's going to be 1,200 and 1,230. No, 1,220 Kelvin, I think. Is that what 947 plus 273 is? Did I just make that up?
Yes, that's right.
Okay, good. Okay. You generally speaking should not trust my mental calculator. It's not always on the level, shall we say. Alright, 737 plus 273, that I can feel pretty confident is 1,010. Unless it's not.
It is.
It's good? Okay. Alright, so then all you have, so like I said, what I would do is I would calculate this bottom part, come up with a number, calculate, take the ln of this over this, calculate, come up with a number, and then do this times that divided by that. And that'll just ensure that you're a little bit safer.
1,150.75 total for everything.
Oh wow. Okay. So EA is, what did you say it was? 1,000 what?
1,150.75.
Okay, so probably 4 sig figs is good enough, but 1,700, 1,151, we'll say. Joules though. Notice this is joules per mole Kelvin, so effectively Kelvin does cancel out here with this. So it'll be joules per mole, but if you want to get it to kilojoules, you'll have to divide both sides by 1,000, or you'll have to divide by 1,000, and that'll give you 1.151 kilojoules per mole, which is actually really small. It's actually really small in activation energy. Makes me think you did it wrong. I was kidding. May I start borrow your calculator, man? Thank you. Oh, what do you know? I got 1,150.7. I was kidding.
Sorry.
No, that was pretty close. You're good. You're good. So that's how you would do that. So you can calculate the activation energy. You can also calculate the temperature at which a reaction doubles. So you could say like, well, the K was initial. Well, if the K2 is twice the amount of K1, you can take the ln of 1/2 and calculate the temperature at which a reaction doubles if you already know the activation energy. So that's a common question they like to ask. All right, so let's take a look at problem 8. I know we're going a little bit past time. I hope if that's not a problem for y'all, but if you do need to leave, that's totally okay. I understand. All right. So here's the deal. is how many elementary reactions are in a reaction mechanism. So, in most reactions, they don't, well, in a lot of reactions, they don't just happen in one step. Sometimes they happen in 2 steps, or 3 steps, or 4 steps, or more. So, the rate of reaction, you have to understand the rate of reaction is always due to the rate of the slowest step. So I'm actually going to write that down because it's so important. The rate of reaction, if I'm writing this down, means you should too. The rate of reaction is always the rate of the slowest step. That's the one that determines where the reaction gets held up. Okay? So if you look at problem 8 and you look at the diagram there, there's 2 bumps. Each bump represents a step in the reaction. So you get an activated complex, and then that activated complex combines, a reaction happens, and you get some products, right? And then those products may react again to go up to a new activated complex, and then collapse down to a final product, okay? And there could be, like I said, there could be 1 bump, 2 bumps, 3 bumps. It depends on what the reaction is and how many steps the reaction has. In this case, this one has 2 steps, or 2 elementary reactions, okay? Now, an intermediate is something that is formed in the process of a reaction, but then reacts to help form the product. So it's not something that there is present, it's not something that's present initially, but it's something that's formed in the, after one step, and then it's used up in the second step. So generally speaking, your intermediates here are going to be this, whatever's present here. Whatever substance are present at this point here, these are called your intermediates. They weren't there to begin with, but they're formed as a result of the first step or second step of the reaction, and then they're used up by the very end. So in this case, there are 2 elementary reactions, so that would be the answer for part A, and then there's 1 intermediate. Strictly speaking, there could be more than 1 intermediate, depending upon how many substances are formed here, but there's only 1 intermediate position in the reaction.
Where are the elementary reactions?
So going from here to here is elementary reaction. So let me give you an example. So let's say, for example, I have A plus B goes to form AB. Okay? Let's say that's the first step, step 1. That's what's represented. That's what's represented by this first section here.
Okay.
Yeah, I start with A plus B. They react, and here I have AB. Okay? Step 2 then happens. And I have A react with AB to form A2B. Okay? So, my final product here is A2B. The transition state here could be something like where A is partially starting to form a bond with B. It's coming together, but it's not completely there. And the transition state up here could be something like where B is more or less bonded with A, but this other one is starting to come in and form a bond with B to give you A2B. But the transition state that says this unstable stage at its highest energy that it needs to reach before it combines to form a new molecule. So now, which step has the higher activation energy? Step 1 or step 2?
Two.
Step 2. And therefore, which step would be slower?
Step 1.
Two.
Step 2. The one with the higher activation energy, it's going to require a lot more energy to get up there, so it's going to be harder to happen, and that's going to be the slower step. Because remember when I showed you that energy diagram with the particles? There's always fewer particles at those higher energy points. So it's to get up to here, it's going to be a lot fewer particles that are much fewer molecules that are going to be able to react with that higher activation energy. So that's going to be much slower. So the second step here is the slow step, and it's the slow step because it has the higher activation energy. Now, the intermediate here is AB, because you notice that if I add these reaction steps together, I get 2A plus B goes to form A2B. In the overall reaction, AB is not present. Intermediates do not show up in the overall reaction. They're formed as a part of one step and then they're completely used up by the end. So that's this thing with intermediates. They don't show up in the final overall reaction. Now based on this particular question, is this exothermic or endothermic?
Exo.
It looks like it's slightly exothermic because the products are a little bit lower than the initial reactants. Alright, so so now I'm going to actually show you how to use rate data to figure out the rate law, or rather how to use the mechanism to figure out the rate law for a particular reaction. So that would be what we're doing in step 9, for problem 9. It says the following mechanism has been proposed for the reaction of nitrogen monoxide with hydrogen to form N2O and H2O. Show that the elementary reactions of the proposed mechanism add up to provide a balanced equation for this reaction. Well, in that case, essentially all we're doing is adding up the two half reaction, adding up the two elementary reactions and coming up with an overall reaction. So that would be like, I have NO plus NO goes to form N2O2. And this will be step 1. And then I'll have N2O2. And that will react with H2 to form N2O and H2O. Okay. Now if I add these together, so this is step 2, this gives me NO and NO, which is 2NO,
Plus H2.
and then at plus N2O2, plus H2.
Is N and 2 O2 will cancel with the other one?
I'm sorry?
Will it cancel with the other one?
Yes, exactly. And I was actually just going to about to ask that in a little bit, but you jumped the gun. Good job. All right. So yes, N2O2, since it's present on both sides, that means it's not actually part of the overall balanced equation. So you can then simply write the remaining equation, which is 2NO plus H2 gives you N2O and H2O. Okay. So that's the overall balanced equation. Now here's the thing. The rate law for a reaction is determined by the rate of the slowest step. Okay? So if the slowest step is the first step, the going back to actually what we said, what I mentioned last session, when you're trying to figure out the rate law for a reaction, you can't go by the overall reaction, because it may or may not be the case. This may or may not be an elementary reaction. In this case, it's not, because we know that there's 2 or more steps to it. Also, another thing to notice is that sometimes the rate laws that we get don't have anything to do, like they completely omit one of the reactants. Okay? So you can't determine the rate law from an overall reaction. However, you can determine a rate law for elementary reactions. For an elementary reaction, the rate law is simply going to be the concentration of one reactant times the concentration of the other reactant times the rate constant. So in this case, for step 1, the rate law for this elementary reaction, I'm going to call this rate 1, is equal to K1 times NO times NO. Of course, since NO and NO are the same, I could also write this as NO squared. And alternatively, I could also write this reaction as simply 2NO. Does that make sense? Okay, good. So now, if I wanted to write the rate law of the second elementary step, I could do the same thing. It would be rate for step number 2 is equal to K2 times the concentration of N2O2 times the concentration of H2. So this is the rate law for elementary step 1, and this is the rate law for elementary step 2. Now, if the first step is the slow step, the rate law will be this. If the second step is the slow step, the rate law will be this. But the only way we can know what the actual slowest step is by actually experimentally determining what the rate law is. So I experimentally determine that the rate law is, say, this or this, and then that tells me which one is the slow step. Now in this case, what are the intermediates of this particular rate mechanism?
N2O2.
N2O2. And there lies the problem with this particular rate law. A rate law for a reaction cannot have an intermediate in it. Because you can't isolate an intermediate. It's used up too quickly. So you can't have an intermediate in a rate law. That doesn't help you. So in a case where you have to solve for a rate law for something where it has an intermediate like this, you have to solve for the rate law in terms of non-intermediates. So now for part D, it says the observed rate law is rate equals KNO squared H2 times H2. If the proposed mechanism is correct, if this mechanism, this step 1, step 2 mechanism is correct, what can we conclude about which step is the fast step and which step is the slow step?
First one, the fastest, and the second one, the slowest.
Yeah. If the actual rate law is rate equals K times NO squared times H2, that means that this cannot be the slow step. If this was the slow step, this would be my rate law, but it's not. Now here's the thing. Let's say I didn't know that this proposed mechanism was correct. How could I prove that this is the same as this? Let me show you. So, here's what I would do. I would solve for the intermediate in terms of non-intermediate. So I've already concluded that because this is the rate law for the actual reaction, this is wrong, right? This is wrong. So it's either this or nothing. This is either correct or nothing is. So I can determine if this is right. If this is right, that means this is the slow step, which means this is the fast step. Fast steps occur at equilibrium. So I have a forward arrow and a reverse arrow here. Fast steps occur at equilibrium. Slow steps will not. Alright, so in this case then, what I will do is I will assume that my forward rate for this reaction is equal to my reverse rate for this reaction. So, if rate 1 is equal to K1 times NO squared, right? Then rate negative 1 is equal to K negative 1 times N2O2. Because if this is equilibrium, there's both a forward reaction, in which case these are the reactants, and there's a reverse reaction, in which this is the reactant. Does that make sense so far? Okay. In equilibrium reactions, the forward reaction and the reverse reaction are both happening, and they're happening at the same rate. That's what it means to be at equilibrium. So if I do the rate law for this forward reaction of the elementary step, these are going to be the reactants, and it's going to be rate equals K, some K, I don't know what it is, times the reactants, which is NO. And it's going to be squared because it's 2 NO, NO and NO. But the reverse reaction is also happening. So I can write a rate law for the reverse reaction, and that'll be rate negative 1 is equal to some other K, I don't know what it is, but I know it's going to be different than this one. And that's going to be time the reactant of the reverse reaction, which is N2O2. So that makes sense so far? Now, because it's in equilibrium, which means the forward rate and the reverse rate are equal, I can set them equal to each other and say K1 times NO squared is equal to K negative 1 times N2O2. Does that make sense? And that means I can now solve for N2O2 by dividing by K negative 1. So N2O2, the concentration of N2O2 is the same as K1 times NO squared divided by K negative 1. Since I've established this relationship, I can now substitute this into this rate law for N2O2. And then that will give me rate 2 is equal to K2 times K1 NO squared, NO squared over K negative 1 times H2. Now since K2 and K1 and K negative 1 are all constants, I can just roll them all into a new constant. I can just say, well, a constant times a constant divided by a constant is a constant, right? So I'll just call, I'm going to say, let a new constant K be equal to K2 times K1 divided by K negative 1. Okay? And if I do that, and these three constants are rolled into one single constant, this rate 2 becomes K times NO squared times H2, which is essentially the same thing that I determined experimentally. So that confirms that not only is this a valid proposed mechanism, but that the second step is indeed the slow step of that mechanism. Does that make sense?
Yes.
So, that's it. We're done.